Welcome. Today, we are breaking down the evolution of wireless technology by comparing the LTE and 5G new radio protocol stacks. Let's start with 4G LTE. The data moves from the physical layer at the bottom through the MAC, RLC, and PDCP layer. Now, let's look at 5G new radio. While it keeps a similar foundation to LTE, the underlying capabilities are heavily upgraded. At the bottom, 5G introduces massive MIMO and beamforming at the physical layer. Right above it, the MAC layer introduces new numerologies to drasters. The biggest structural change in 5G is the introduction of a brand new top layer, SDAP, or Service Data Adaptation Chirps. When 5G was first deployed, carriers used an architecture called non-standalone, or NSA. In this setup, the 4G LTE tower acts as the control plane anchor. It handles the critical back-end signaling, network connection setup, and routing instructions for your device. Now, let's look at 5G new radio. While it keeps a similar foundation to LTE, the underlying capabilities are heavily upgraded. At the bottom, 5G introduces massive MIMO and beamforming at the physical layer. Right above it, the MAC layer introduces new numerologies to drastically lower latency. To understand 5G, we have to look at the math of a radio wave. 4G LTE uses a rigid, fixed subcarrier space. But drop down to 5G new radio, and the wave physically morphs. Instead of using a rigid mold, 5G introduces scalable numerology. Look at the math. As the frequency spacing doubles from 15 to 30 to 60 kHz, the slot duration shrinks proportionally. By letting the radio grid flex and compress, 5G optimizes itself for everything from basic browsing to instantaneous robotics.
Transitioning from the physical radio wave to total network performance reveals a massive leap in raw capability.
In peak data rates, 5G rockets to a staggering 20 gigabits per second download, nearly 7 times faster than LTE.
Traffic density gets a monumental upgrade too. 5G supports 1 million connected devices per square kilometer, a 10-fold increase. By unlocking high-frequency millimeter wave bands and deploying native network slicing, 5G transforms the architecture entirely. Managing high-speed 5G data requires an advanced protocol architecture, starting with incoming user IP flows. Traffic feeds straight into the SDAP sublayer, which standardizes incoming service data packets instantly. SDAP maps the traffic into specific data radio bearers based on quality of service flow identifiers. This ensures low latency VoIP, high bandwidth video, and web browsing each get optimized, prioritized paths. Managing high-speed 5G data begins at the user plane with incoming application IP flows.
Traffic feeds into the SDAP sublayer, instantly sorting packets based on quality of service rules.
SDAP dynamically maps each stream into specialized data radio bearers to preserve priority.
Once mapped to bearers, data drops lower down the protocol stack to be processed.
In legacy LTE, sequential RLC segmentation creates a processing bottleneck, increasing overall latency.
5G NR eliminates this delay by using pre-processed headers for an instant handoff. This shift allows the MAC layer to handle concatenation in parallel, speeding up delivery.
Moving concatenation to the MAC-C layer enables the parallel processing vital for 5G speed.
In legacy LTE, sequential data assembly creates an inherent processing bottleneck. However, 5G NR eliminates this lag by processing protocol headers in parallel. To see how this works, let's examine the exact packet header structure.
LTE forces data to wait until the exact payload size is known. Only then can the RLC header be generated, delaying delivery to MAC.
5G NR fixes this by creating independent RLC sub-PDUs beforehand.
This allows the MAC layer to concatenate data instantly upon request.
Moving concatenation to MAC enables the ultra-low latency defining 5G networks. To see how 5G speeds up processing, Let's examine the exact packet header structure.
Legacy LTE forces data blocks to wait until the final payload size is known. Legacy LTE forces data blocks to wait until the final payload size is known.
Conversely, 5G NR fixes this by building independent RLC sub-PDUs completely in advance. This allows the MAC layer to perform instant concatenation the moment it is requested. Moving concatenation to MAC enables the parallel processing vital for ultra-low latency 5G.
At the user plane, incoming application data streams must first hit the SDAP sublayer.
SDAP intelligently maps these user IP flows directly into prioritized data radio bearers. In non-standalone option 3X, the legacy 4G core still anchors the network control plane. Traffic splits at the 5G secondary node, routing user data paths across both generations. Migrating to standalone option 2 creates a direct, unanchored connection to pure 5G hardware. Data now streams straight through a highly modular, cloud-native 5G core network.
Each isolated slice dynamically optimizes latency, throughput, or capacity for specific industrial demands.